All right, so this is section 2.6, mathematical models building functions. Our first learning objective is to build and analyze functions. Okay, finding the distance from the origin to a point on the graph. And this is, as I put your quiz together last week, this is definitely on your quiz. So if you let P be a point on the graph, and your graph is y equals x squared minus 1, we are going to find the distance d from P to the origin as a function of x. Then we are going to find the distance if x is equal to 0. And then we're going to find the distance if x is equal to 1. And then we're going to find the distance, just for fun, if x is equal to root 2 over 2. Then we're going to use a graphing utility and graph the function. All right, so the picture of this looks like, here I have my nice little parabola. It's a standard parabola translated down 1 unit, so go ahead and draw the sketch of this. And I want to find distance from the origin to any point on my function. All right, so if we take a look at our distance formula, the distance formula says I'm going to take the x coordinates of our 2 points and subtract them and square them. Our y coordinates from the 2 points, subtract them and square them. So all I want you to write down is this d equals and then x squared plus y squared. Because we're at the origin, it simplifies our distance formula down because we're just subtracting 0 and 0 from the x and the y. So our distance from any point on this, our graph, is square root x squared plus y squared. All right, so take a look at what information we know. We know y equals x squared minus 1. So in our distance formula that we just simplified down, we're going to take the y value and replace it with x squared minus 1. Then we're going to multiply this out. We're going to say x squared minus 1 times x squared minus 1 and combine it with our x squared value here. Okay, so when you multiply this guy out, you get x to the 4th minus 2x squared plus 1. Minus 2x squared combines with this x squared to give you minus x squared. So you have square root x to the 4th minus x squared plus 1. So that is our answer to A. So if you want to put A right there, that's perfectly fine. B, what is D if x is equal to 0? So now that we have our distance equation, we're going to start plugging in values and finding the distance. So if D is equal to 0, we plug 0 in here, and these go away, they become 0, and we just get square root of 1, and that is 1. What if x is equal to 1? Then I get 1 minus 1 plus 1, which is 1. And if you look at your graph, look here, if x is equal to 0, then my distance from the origin is 1. If x is equal to 1, which is right here, then my distance from the origin is still 1. So what is D if x is equal to square root of 2 over 2? Well, that seems like a crazy guy to put in there. So we just put it in because we know how to plug numbers into a function. Root 2 over 2 to the 4th power minus root 2 over 2 squared plus 1. When you simplify all that down and take the square root crazy enough, we get root 3 over 2. Awesome. Thank you. All right, so the next thing we're going to do is use a graphing utility. So go ahead and get out your graphing utility. Okay. So if I'm going to graph this guy and find the local minimum, we want to make sure we are just looking at the values that are greater than or equal to 0. Because this is a parabola, it does have a local min less than 0. That is the same distance away. So we're just looking at distances that are greater than 0 because there are no distances that are negative. It's just not allowed. Okay. Next, oh, sorry. Let me wrap this up. So the minimum distance is 0.71, comma, 0.87, rounded 2 decimal places. So the distance is a local min at 0.71. All right, so next problem. Area of a rectangle. So a rectangle has one corner on the graph of y equals 25 minus x squared, another at the origin, a third at the positive y-axis, and a fourth on the positive x-axis. So go ahead and write this down. I'll give you guys a moment. You guys can write down A, B, C, and D as we are solving them. So don't feel like you have to write them all down at once. Those of you guys at home can write this down, pause it, and write at your leisure. So we're going to express the area as a function of x. We're going to find the domain, and we're going to graph it, and then we're going to find the x value that makes our area the largest. All right, so the hardest part is this A, expressing the area of the rectangle as a function of x. The first thing we have to remember is how do we find the area of a rectangle? The area of the rectangle is the distance along the x-axis that our x-coordinate takes us, times the distance along the y-axis that our y-coordinate takes us. So it's x space times height, or x times y. This is the most difficult thing to figure out. So if you get a problem like this again, you will now know, oh, it's just the x-coordinate times the y-coordinate. We are going to replace the y value with 25 minus x squared because we know that we are on, our y-coordinate is the one that goes with, that's going to be on this parabola. So we do that and we distribute out the x and we get 25 minus x cubed. Not too bad. So area of our rectangle as a function of x is 25x minus x cubed. Now we have to look at what domain is going to be reasonable for our area, and well, we cross the x-axis at 5, so we could definitely not have any x values that are larger than 5, and we know that because we are on, we have a corner on the origin, this corner stays fixed, so we are not going to go less than 0. So our x value or our domain is between 0 and 5. Okay, so let's take a look. You guys all have your graphing utilities out. Let's go ahead and graph this function, 25x minus x cubed. And we're going to put the sketch of that graph on our paper. And remember, we only are caring about the values that are between 0 and 5 on our x-axis. So we are not going to take a look at anything below x equals 0. And let's make sure we set our window so that we can see the very top here. So we want to make sure our y max is at least 50 on our graphene window. And we're going to go ahead because after we sketch the graph on our paper, we want to find the value of x that has the largest area. So we are going to find the point that maximizes our area. We're going to use our graphing utility. We're going to calculate the maximum. And we find that happens at around 2.9. And that gives us an area of about 48. Okay, next problem, and you guys feel free to abbreviate this so that you don't have to write every single word down, but it's important. Definitely we need the picture. A manufacturer of children's playpens makes a square model that can be opened at one corner and attached at right angles to a wall or perhaps the side of a house. If each side is 3 feet in length, the open configuration doubles the available area in which the child can play from 9 square feet to 18 square feet. And that's this figure right here. So if this were a square and you didn't have the wall, it would only be 9 square feet. If you use the wall as the side of your rectangular prism, then it doubles your area. Now suppose we place hinges at the outer corners, right here, to allow for the configuration like we see in this little figure. So almost a house-shaped figure. We're going to build a model that expresses the area shown in figure 66 as a function of the distance x between the two parallel sides, so between this side and this side. Let me pause for a second so you guys can write. All right, so if we want this x value, we have to look what information do we know? We know that we have a right triangle here. One of the legs of the right triangle is half of x. The other leg of that right triangle is h, and our hypotenuse is 3. So if we go x over 2 squared plus h squared equals 3 squared, that would be our nice Pythagorean theorem formula. We simplify that down so we can get a value of h in terms of x. So our height in terms of x is 3 squared minus x squared over, or x over 2 squared. And then we simplify that down further. This is 9, and this is x squared over 4. And then we find a common denominator, so 9 becomes 36 over 4 minus x squared over 4. So we can get 36 minus x squared over 4. So when you take the square root of this, 36 minus x squared doesn't have a perfect square. It is the difference of squares, but it doesn't have a perfect square. But the 1/4, when I take the square root of it, becomes 1/2. So now I know what my height is in terms of my distance x. So now, when I look at the area of this enclosure, we have the area of the rectangle here, which is 3 times x, and we have the area of the triangle, which is 1/2 base, which is x, so 1/2 base times the height. And we got that wonky height. All right, so our area is the area of our rectangle, which is 3 times x, plus the area of this triangular shape, which is 1/2 base, which is x, times height, which we found was 1/2 square root 36 minus x squared. Looking at domain, what is the smallest x value we could possibly have? How small down can we get that x? Can we, and ask yourself, can x be negative? Nod yes, or shake your head no. Can x be negative? Can this distance between the sides of your pie pen be negative? No. So we are definitely going to have an x value that's bigger than 0. And then what is the biggest x value that we could possibly have? What if these gates were to swing shut and get you the largest value? Oh, that's 3 plus 3 is 6. So the very most this x value can be is 6. So our domain goes from 0 to 6, or open not included 0, comma 6, also not included. Okay, so if I have x equals 5, so if I make it 5 feet across, let's find the area of our little playpen. So we're going to take our area equation and we're going to plug in 5 for x. So that gives us 3 times 5 plus 5 over 4 times the square root of 36 minus 5 squared. This is a simple calculator chug. If you don't know how to do this, take a moment right now, chug this in your calculator. If you don't get out 19.15, let me know right away so that I can help you with that. All right. So let's see what the graph looks like and see what the maximum area we can get out. So if we can graph it on our graphing calculator, we can find the maximum value, so we know how large our distance between the sides can be, and then what the most area we're going to get out of it is. So we want to make sure we look at just values between 0 and 6, and then make sure you adjust your y max so we can get to the top of our arc. So just to remind you, we're putting in our equation for a, so that's the 3 times x minus, so if we go back, so we're putting in 3x plus x square root 36 minus x squared, all divided by 4. Make sure you have parentheses around the numerator here, so when you divide by 4, it's this entire item divided by 4, because it'll change your value if you don't. Use your calculate operation on your graphing utility, and you will see that x equals 5.6-ish, rounded, will give you an area of 19.8 square feet. And that's all for today.